good? Okay, yeah. So, you know, it's up to if you guys want higher quality control on your lecture video, you're looking at it. You're welcome to grab onto the camera. Okay, have we started the next homework? Show of hands. Yeah, hopefully it's a little easier than the last one. I know the last one was very theoretical, lots of math problems. This one's about 50-50, right? So the first two problems are completely math, the second two problems are a little bit closer to applications. In fact, I took two pretty recent methods from machine learning and put them on your problem set. So these haven't appeared in CS205A in the past, which means there's some odds that I make typos, but I don't ever make mistakes, so probably not. Speaking of which, several mistakes from the last lecture were posted on Piazza. You should look. Thank you to those of you that helped me out. The main thing you should know is thankfully no critical mistakes were made, but there were one or two sign problems. And I'll update the lecture notes as well, because I think the reason that I made those mistakes is because they're in my lecture notes. So let's say we'll agree that I'll fix them by Friday. And you guys can ping me to ask to make sure that they've been fixed. Basically, the main issue was just that matrix H sub v, that reflection matrix I had, should have had a minus sign in front of it. But if you remember, the only thing that mattered was that H sub v preserves angles and lengths, and thankfully negative of a matrix that does that still preserves angles and lengths, so the rest of our lecture is okay. So, apologies, if you ever catch a mistake in lecture, you should stop me right then and tell me, because I'm going to keep using it. And it's just going to be turtles all the way down. You might as well, you know, I'm going to be building on a shaky foundation, it's going to be awkward for everybody here, so just stop me. Anyway, any questions about procedural stuff, last lecture? Nothing? Okay, great. So, today we're going to embark upon my favorite part of CS205A. And in fact, the thing that I use the most in my own research, which is solving for eigenvalues and eigenvectors. And eigen, lots of other things. By the way, if I use the word eigenfunction, that's because that's the word that I use in what I do. And when I say eigenfunction, I really mean eigenvector. Okay, so we're just going to identify those up front. Okay, so on day one, I asked you guys to name two applications of eigenvectors, and you couldn't. So I decided to spend today's lecture mostly justifying why the heck we care about eigenvectors, why we should compute them, and then our next lecture is going to be about how to compute them once we have a good, thorough understanding and warm feelings of all of the exciting things we can do with eigenvectors. Right? So first of all, I suppose I should have added a slide at the beginning of this lecture making sure you guys knew what an eigenvector of a matrix is. So let's do that really quick. I think it's later in this lecture, but that's okay. An eigenvector is sum v not equal to 0. That part's key. If you ever give me something equal to 0, you will receive 0 credit. Such that there's some lambda with a v equals lambda v, right? And hopefully this equation is super familiar to you guys from Math 51 or equivalent prerequisite course. Right? This is the thing that we're trying to solve for. This says that if I take v and I hit it with my matrix A, it's the same as just scaling v by some lambda, and any v that satisfies this relationship for any lambda can be 0 by the way, is an eigenvector of A. Okay? So there's our definition. And of course, the question that you should have asked in Math 51, but apparently not very many people did, was why the heck do we care about this formula? And why is this a property, right? I could have said AV equals cosine of e to the a lambda v. It's God knows what formula. Why is this one so important? And why do we spend so much time trying to solve eigenvalue problems, write down characteristic equations and all these polynomials and this and that, and then computing these things? Right? You literally waste, I was looking at the Math 51 syllabus, you waste 3 weeks on this stuff? So let's figure out what we're going to do with all these eigenvectors before we get any farther. Okay. By the way, although I am personally in love with functional analysis, we're not going to talk about all of the fun mathematical things you can do with eigenvectors. We'll try to restrict ourselves to computer science applications, which I think is probably just as well for the audience I have here. If you want, come to my office hours and we'll chat about all the magical things you can do with like elliptic equations and PDE and this sort of thing. Right? What is this? Sobolev spaces are really cool. Anyway, but for us, let's say that I'm doing a medical survey and I have a lot of different patients in my hospital and I'm trying to understand something about heart disease, so I start asking them questions about their life and I'm trying to cluster similar patients. It's a very practical problem and one that certainly shows up in machine learning and big data, which is what we all want to do. I got an email about this today. So let's say in the end I get a bunch of data points about each of the patients in my hospital, and we'll just call those points x sub I. Right? And so maybe the first component of x sub I is the age of my patient, the second one is their weight, their blood pressure, their heart rate. My x sub I is probably pretty embarrassing, hopefully yours is better. And in the end, you have this big cloud of points in, I guess, R4. Right? And our question is, what do these points look like? Because 4 dimensions is awfully hard to visualize, if nothing else. Right? And how do I know if two patients are similar? These are all sort of questions that we should care about. And there's some fundamental issues here that you might not think about initially. Right? So first of all, let's say that I have two data points, right, x and y, and they're in R4, right, because we collected age, weight, blood pressure, heart rate. By the way, really, if we're doing statistical things, we should remember that these are positive numbers and those should be treated slightly differently, but I'm going to ignore that for today. But anyway, don't think I didn't remember that. But let's say that we have two data points, x and y, and they're in R4, and they collect this data. And I want to measure how similar I am to Leonard, right? Leonard is y, naturally. And so I subtract the two, x minus y, and hopefully these are far away, because Leonard looks like a healthy guy, and I take the norm. Does this norm make any sense? No, right? Because what did I do? I just took the difference between our ages and squared it, and then I added that to the squared difference between our weights, and then I added that to the squared difference between our blood pressure, right? So in the end, I'm adding like years, pounds, and millimeters of mercury, or whatever the heck you use for blood pressure, and this doesn't make any sense. I can't add these things. So I need to find a reasonable set of axes that I can use that represent my data points in R4 in a way that makes sense, and I can use norms and angles and dot products and all these things. I think this is a very practical problem, right? Even if you didn't like all the epsilons and deltas in the first problem set, I'd say this is a very reasonable question to ask. So our goal is to find correlations between these different dimensions for now. Right? So what do I mean by this? Well, let's say I'm older, then chances are I'm going to have a higher blood pressure and a worse heart rate. You know? And perhaps if you're heavier, these things are also the case. So I guess I'm using negative examples. If you're healthier and you have a smaller weight, then maybe your blood pressure is lower and you have a happier heart rate. Of course, these things are all fuzzy, right? You have all these data points that in the end are somehow correlated, right? They make this pattern that looks kind of like a line, but it's not quite. And our job is to extract this axis here. By the way, how many people think they've probably seen this story before? I've already answered it. PCA is a phrase we do in our science. Nobody? Oh, one or two. Okay, good. I mean, this should be familiar, but hopefully the math background is a little bit different. So we're going to simplify our problem for now, and then after we talk about the support vector, the singular value decomposition of a matrix, we'll come back to a more general version of this problem. But for now, I'm going to say that I approximate my entire space of data points with just a single line. And my job is to figure out which single line approximates my data points the best. Right? And so in particular, we're going to assume that all of our xi's, remember that xi is that pile of things that's like blood pressure, heart rate, how much your parents watered you when you were little, and now I want to project those all onto a single vector v. Right? So I'm going to say that xi is approximately some ci times v. Now first of all, does the norm of v have any meaning here? No, right? All I care about is that like 2 units of blood pressure correspond to 5 units of age or something. Those are the sorts of statements we're writing down, right? And since this is sort of a ratio thing, like scaling our whole unitism up by 10 still is going to represent the same ratios, right? So without loss of generality, W log, we can write down that V should have unit length. Cool. And remember our notation from our last lectures that unit vectors are always going to have this. So in the end, our job is to find a unit vector V that approximates the entire data set pretty well, where there's sort of 2 unknowns here. right? Each of the xi is going to have a different ci, and we also don't know this vector v. Cool? Okay. By the way, I got a lot of questions that, from people that were sort of lost during lecture because there's lots of like equations and numerical stuff in bookkeeping that we have to do. Such is life in the city in numerical analysis. There's just a lot of algebra. But what I encourage you to do is that when I make a problem statement like this, and I say like, this is the unknown and these are the knowns, I want you to put a big box around that in your lecture notes. And every time you're lost, I want you to go back to that box and have your little dictionary ready to go of like, this is what we know, this is what we're trying to compute, and this is why I care. And then I feel like if you at least have that much in mind, if you skip a step or two, you won't be just like totally lost forever, okay? That's my advice to you. Also, just raise your hand and ask me if you're lost, like, for God's sake. So anyway, thankfully from our last lecture, we developed some machinery for computing these numbers c sub I. Right? So let's say that I found an axis v, or somebody gives me an axis v hat here. Then what is ci? How do I compute it? Most of you guys are here on Monday, so how do I compute c?
Projection.
Projection. Exactly. Basically, we're taking each of these vectors of x and we're projecting it onto v hat. Yeah? And so, in particular, what is our formula for ci? I think I put it on the slide here. Yeah. Well, since v is a unit vector, it's simply the dot product between v and your data point xi. Right? Remember the denominator goes away because this is v dot v here. And so this is going to be the formula for the ci. And now our job is just to find v. No problem. So how are we going to do this? Well, hopefully by now you figured out that your instructor really likes to write all problems variationally. Right? That sort of, I like to play this game where I write down something that looks like minimize, E such that some set of conditions holds. And then this is what's going to be our guiding light in terms of how we derive all of these different numerical techniques. And this is no exception to that rule. Nor is almost anything else in this course. I started writing course notes again and noticed this is like a pattern that permeates my treatment of numerical stuff. By the way, other people do this differently. If you look in your textbook, there actually aren't that many variational problems. Such is life. This is what I like. Wait, so in particular, we have all these data points xi, right? These are all of our subjects in our hospital, all these different information about their heart rate, blood pressure, whatever. And then we want to approximate that with a projection onto v. So what is our unknown here, by the way? V. Yeah, gonna keep asking. And what are our constraints? Well, we decided that the norm of v is going to equal 1. Right? Did we necessarily have to do that? No, but then our projection formula is going to get more complicated. Right? So I'm going to favor adding this constraint that norm v equals 1, and then our projection formula is going to be easy, as opposed to the other way around, removing that constraint. Right? And we know that we'll get the same answer regardless. Okay, so let's do a little bit of simplification. Right. So here's our optimization, and in particular, the energy that we care about is the sum over all of our data points of the distance from the data point to his projection onto v hat of the same data point. Yeah? So we understand this energy, right? It's just the distance between the thing that I observe and the approximation that I'm about to make, and I'd like that approximation to be small for all I. Yeah? How many people are following, by the way? Great. Okay. So let's expand this thing. So first of all, we have a formula for the projection, right? We had that on the previous slide. So let's plug that in. So now we're going to have xi minus, and then what do we get? We get xi dot v, oh oops, it's a hat, right? Times v squared. By the way, for today's lecture, we're only going to be using 2 norms, so I'm going to drop that subscript again. I should keep reminding you guys. On your homework does not use the 2 norm, nor does it use the p norm of the vector in problem 1. I saw both of those during office hours this morning. You cannot assume anything on that vector norm except that it satisfies the triangle inequality and is a norm. And Leonard, you have to do your answer rigorously. I didn't like that email. No picture drawing allowed. Well, you can draw pictures, but it has to come with math. Okay. So, by now you guys can probably more or less predict like the 3 tricks that your instructor really likes to do when you see expressions that look like this, right? And one of them is interpreting this norm squared as something dot product itself, and then foiling that product, right? Just expanding it out. So let's do that. And so this thing is still a sum over I for now. What? Well, xi dot itself, which is just the norm of xi squared. minus 2, and then this is just a scalar, right? So xi dot v hat times, and then what is this? Xi dot v hat. Ain't that convenient? Right? And then plus this guy dot itself. Right? What is that number going to be? Well, you get v dot v is just 1, and then you get this thing twice, so it's still xi dot v hat. Yeah? Ain't that? Isn't that funny? This doesn't normally happen when we take we extend this stuff out. Okay? So in particular, I can cross him off and cross this 2 off. Yeah. And so in the end, I want to minimize something slightly different, which is xi squared minus xi dot v hat squared. Okay. So there's our energy. And in particular, again, I guess I should be a little more explicit about asking, what are our unknowns? Our unknown is this v hat, right? So in particular, does this energy term matter? No, he's just a constant shift. What matters is this guy, right? So minimizing this sum is equivalent to minimizing this sum, right? Because they're equal. And since there's a minus here, that's equivalent to maximizing this last term, because this is just a constant. Yeah? So, hopefully that's what's on my next slide. Yes? So in particular, right, what's going to be our problem? Well, right, so this thing, we'll say we have some new energy, E tilde, and here is the sum over I of xi dot, that's a vector, dot v hat squared. Right? And what are the xi dot v hats? Well, one way to think about this is, let's say that you have x1 you have this matrix, right? x1 transpose, x2 transpose, and so on, right? So I just take all of my data points, I flip them on their side, and I stack them vertically, right? We'll call this thing capital X transpose, because we like to think of our x's as vertical vectors. By the way, this shows up on your problem set on number 4. Yeah. So what is this thing? Well, it's the dot product with v, and we know how to encode a bunch of dot products. We just stick this v here, right? Because remember what's going to happen. You'll be moving this way on x and this way on v, and so this is just a bunch of dot products, right? And in the end, you're just squaring them up and summing them. Well, what is our notation for square a vector and sum it up? Well, it's just norm of x transpose v hat squared. Yeah? So this is the thing that we want to maximize. Okay, and hopefully that's what's on here. Yes, it is. And we still need, in fact now, our choice of having the norm of v hat equal to 1 became critical. Right? Because what would happen if I removed our constraint? What is the minimum of this energy if I don't have the such that line here? 0. Yeah. Why is it 0? Because if I didn't have the norm of v is 1, then I can just choose v equals 0. We know the norms are positive, so I just minimize my energy, but I got a really boring thing out. Yeah? So this constraint that the norm of v squared equals 1 is critical here. And it's critical for 2 reasons. 1, because this will give you a boring answer if it's not there. And 2, because this entire proof depended on this formula here for the projection, which only holds when v is unit length. Cool. All right, so we just transformed our problem into something pretty nice. And in fact, I would say at this point, we can apply another one of Justin's favorite tricks to finishing off our proof here, which is going to be what? Lagrange multipliers. Yeah? Right? They're literally 3 hammers in this class. We're just going to keep using them. You should go down, anytime you're stuck on your homework, go down the list of hammers that Justin uses. And chances are, 80% of the time, you're going to be able to figure out the problem. So what is the Lagrange multiplier function here? Well, he's capital lambda, right? And he's a function of v hat and an additional multiplier which we'll call lambda. Yeah, so we'll say that this is the norm of x transpose v hat squared. Remember, and then how do Lagrange multipliers work? We're going to add a second term to our energy that looks like our constraint. Yeah? And so in particular, let's say that this is lambda minus lambda times, I always get this backward if I want it to look like an eigenproblem. V v hat transpose v hat minus 1. Okay? So this is saying that you want critical points of this function with this thing being equal to 0. By the way, what is lambda? Scalar, vector, matrix, tensor, some sort of animal. What is lambda? Scalar. Thank you. Because there's only one constraint. The norm of this thing is 1. Yeah. So what is the gradient of the Lagrange multiplier? Well, hopefully by now we're getting a little bit faster at taking gradients of these energies that are a bunch of kind of linear quadratic looking things, right? So in particular, right? Remember that this guy is equal to what? V hat transpose x transpose v hat. Yeah, we've gone through this little trick a few times now. So what is his derivative? Well, it's nothing more than 2x transpose v hat. Yeah. And what is the derivative of the second guy? Well, this is a constant, and we're taking the derivative with respect to v hat right now. I should pull v hat there. And so this is going to be minus 2 lambda v. Yeah? We've played this game a few times now, so I think I'll skip the nitty details. If you're lost by this step by now, you should come talk to me and we will go through it and make sure you understand it, because this is critical. Okay. And because we want to minimize this energy, we know that the derivative is equal to 0. Yeah? So in the end, I can move this term right hand side, I can divide by 2, and what do I get? I get that x transpose v hat is equal to lambda v hat. In other words, I want an eigenvector of xx transpose. There we go. Now we have inspiration for why we might care about eigenvectors. By the way, which eigenvector do we want? Right? I mean, the xx transpose in general might have a bunch of eigenvectors. We haven't proven that yet, but it might. Well, we know that in the end, our energy looks like this, right? So let's maybe I'll section off, use the board here. Right? Our energy looks like v hat transpose x transpose v hat, right? And we just showed that x transpose v hat at the critical point, not in general, but at the critical point, is equal to lambda v hat. So I can plug that in, right? I get v hat transpose, and then over here I get lambda v hat again. Right? Just by kind of grouping that a ways. So in other words, my energy is equal to lambda v transpose v, and we know that v is a unit vector, so this is just 1. Right? So the energy at my critical point is this lambda value. So if I have more than one eigenvector, which might be the case, right? Lots of matrices have lots of v's that satisfy this relationship. I want the v where lambda is the biggest, right? Because I'm trying to maximize this energy, and this energy at the critical point is actually equal to lambda. Cool? Cool. By the way, what does this tell you about, what does this tell you about lambda? Can lambda be negative? No, because lambda is equal to this norm, and norms are positive. Okay. Yes, Catherine.
So if we get a big lambda, that means our energy is just very large. So that's what we want.
Yeah, because we're trying to maximize this thing.
Okay.
Yeah. By the way, so when we talk about PCA, if you're a statistician, there's you can either minimize variance or you can maximize some other thing, and these are, we'll come back to that later. Okay, so again, our end goal is we want the eigenvector of xx transpose with the largest eigenvalue. We're going to learn in our next lecture that this is the easiest possible problem to solve on a computer, like ever. Yeah? Yes, sir.
I'm sorry, so what was the relationship to this, to the health data again?
Ah, right. So the way that this works is that you think of the columns of X as a bunch of patients in your hospital, right? So each column has, say, 4 numbers, which is just like age, blood pressure, heart rate, whatever, weight, right? And in the end, we want to project those 4 numbers onto a single axis that somehow is as good a projection as possible, right? That accounts for as much variance as you can. Right, so we wrote down this optimization here, which said that if we can only choose one v here, we want the v to be the best where each xi is approximated well with his projection onto that v. Right? And then so our optimal point for minimizing this energy is this V is exactly the eigenvector of that sex transpose with the largest eigenvalue.
So you just kind of reduce the number of dimensions in the data.
Exactly.
Okay.
In fact, dimensionality reduction is the name of this technique in robotics. Any other questions? Because we're about to move on to other exciting applications of eigenvectors. Yes?
So in that summation, you want to make it you want to make the terms as small as possible, so we're minimizing the one on the right and maximizing the...
Yeah, so we minimized him, right? And then in the end, we simplified him to this other expression, and look, this minus sign is p, right? So minimizing minus something is the same as maximizing plus that, right? And that's what we did. Cool. Anything else? Great. I like these questions. If you are ever stuck, I want you to stop me. Okay? All right. And we call this the first principal component. By the way, what do you think the second principal component is? Yeah, the next one is Eigenvalue, right? So if we want two axes, it's simple as computing more eigenstuff. No? Okay. And we will actually prove that once we have the SVD under our belt. But for now, we don't. So just like. Okay. So now, let's move on to a completely different application of eigenvectors. And that's physics. So I am no physicist. If you are, I apologize in advance because I'll probably get it wrong. But such is life. So to me, physics is basically boils down to two equations. The first one is one of Newton's laws. I won't even guess which one because there are three and that's a big number. But it's F equals ma. Right? So if you think of x as the position of a particle, then this is the total force on that particle is equal to his mass times his acceleration, which of course is just the second derivative of time. Hopefully you've all seen this formula somewhere. Yeah? And there's another handy formula, which is the force of a spring. Right? So in general, let's say that I have two particles that are connected together by a spring. We'll call those particles x and y. Right, so let's say here I am at x, here's x, and here's y, right? Then the force that y feels from this spring is proportional to, so obviously it's pulling in the x direction, assuming that this spring is yanked out. By the way, these springs have natural length 0. We're not going to worry about what happens with this. Actually, we'll come back to that later. Then all you do is you subtract these two guys, and the force pulling y toward x is just proportional to the difference, right? And one of Newton's other laws says that, in this case, the force attracting x toward y is the opposite. Right? So in particular, this force is linear in the set of positions. Right? If I give you like x and y as just one big vector in R6, right? Each of these points is in free space. Then we know that we can compute all the forces, right? Also going to be one big vector in R6, just as some linear operator on the x's and y's. Yeah? Cool. All right. But unfortunately, we have a second derivative hiding in here, and that's a little bit yucky. So let's get rid of that. We can do a usual hack that we do in physics, which is we're going to reduce everything to a first-order system. So here's the trick. Well, what is the first derivative of x? Well, it's the velocity. Yeah? So let's promote the velocity to another variable in our system of equations. Right? So now we have a first-order system of equations. This is a really slick trick, by the way, in case you haven't seen this before. This like blew my mind in undergrad ODE class in like 2005. Yeah. Okay. So right. So now we're going to stack the x and the v in one big vector. We're going to take its first derivative with respect to time. What is the first derivative with respect to time of x? Well, it's v. Right? And we can encode that, right? So we're going to put x and v on the right-hand side, and we'll just put the identity matrix in the upper right side block here, right? And this is saying the first derivative of x with respect to time is v. And what is the first derivative of v? Well, it's the acceleration, but we know F equals ma, right? And we know that our forces, right, are just proportional to some change in positions, right? So that's some matrix K, that's just subtracting off positions, and then we divide by mass. Right? F equals ma, same as force divided by mass equals acceleration. Hopefully I don't have to write that one down. And, right. So in the end, you get this big matrix system that says the first derivative of x and v is equal to this thing on the right. Do you all believe me? That's cool? So it turns out anytime you have like an ODE in like 4 billion variables, or 4 billion different derivatives, you can always just keep applying this trick to make it into just a single first order problem. Is that cool or what? So, Let's generalize a little bit. So in general, I just showed that even though we had a second derivative system, we can write it like this. The derivative of some vector with respect to time, we're going to call that x prime, is equal to a matrix. In our case, that thing with the identity on the right-hand side and the masses and differences down here, times the same vector. It's a pattern that shows up a lot. Simulation and other physics. Right? Now later on in this class, we're going to learn how to do time stepping for physics. So if you have really complicated dynamical systems and these forces are changing as a function of time and position, we'll be able to deal with that. But for now, this is just a linear operator. And in fact, this shows up a lot in solving things like the heat equation and so on. By the way, spring forces don't show up in the heat equation, but similar looking things. Nicer, in fact, positive definite things. Okay. Oops, I guess I went from capital X to not capital X. Such is life. Okay. So again, x prime is equal to a times x, right? That's the ODE we're trying to solve. And maybe just for fun, I'm going to write down all of the different eigenvectors of this matrix A. Right? I can certainly do that. A is just a matrix, so I can compute all of its eigenvectors, and we'll call all those the x sub i's. Right? And then we're going to say at time 0, right? The positions of our springs at time 0. We'll say that those are just going to, maybe we can write them as a linear combination of the eigenvectors of A. Do you see what I did there? I did a change of basis on you by accident. Not by accident, very much on purpose. Right? Is that originally I wrote down the configuration of my system just as points in 3 space, but now I'm going to write it down in the modes, or I should be careful, the eigen stuff of this matrix A. Right? I haven't proven that I can always do this, but let's say I get lucky and my initial conditions are such that I can write x of 0 as a combination of eigenvectors of A. Yeah? Then what can I do? What can I do with this system? Well, it turns out I can solve it in closed form. I can just write down the solution to this first order differential equation and not have to do any time stepping whatsoever. Right? And in particular, well, how could we get there? Well, let's say that we're just in one variable, right? So never mind all this matrix stuff, because matrices are hard, right? That's, I think, a reasonable takeaway so far from this class. Let's say that I had a function that looked like dy over dt equals a y. Yeah? Just good old high school math. What is the solution of this? Well, hopefully you can guess that y equals c e to the at. Did I do that right? Yes, right? Because when I differentiate with respect to t, an a comes out, and that's what we want. Yeah? Cool? Yeah? This is familiar? Yeah. Okay. So I can extend this, this relationship just a little bit, and actually solve this ODE with all these matrices in closed form too. In particular, I claim that x of t basically has exactly the same form. Now, how did I get that? Well, you can kind of guess it based on this form. And of course, the nice thing about the fundamental theorem of uniqueness and existence of ordinary differential equations, aka like the reasonable thing you would guess about equations, is that if I can guess the form and then check that it satisfies my original equation, I'm done. Right? So let's check that it satisfies our equation. Right? So we have x of t, and I'm going to write this as sum over I of c I e to the lambda I t times the vector x sub I in this case. Okay? You agree that this and that are the same? This is a function of t because of this guy, right? Well, first of all, does it satisfy our initial conditions, x of 0? Well, if I put e to the 0 here, what do I get? Well, I just get the sum of ci xi, which is exactly what I wanted. Yeah? And now if I differentiate